Hi, I'm Bruno, and today we're talking about specialty paper. When we say paper, people immediately think of a notebook, maybe a receipt, or something fragile like low tech. The truth is, we spent decades inventing these synthetic alternatives only to realize that if you engineer the microstructure of wood pulp just right, it has special properties like thermal resistance, controlled porosity, things that are incredibly hard to replicate with plastics. So today, let's start with the one that sounds like the most counterintuitive: electronics. Copper clapboard based paper. Well, if I'm designing a printed circuit board, a PCB for example, my main concerns are conductivity, heat, and rigidity. That screams like fiberglass, copper, and resin. But where does paper fit into the backbone of a computer, you might ask? Well, to get this, you have to picture a standard circuit board. It's a sandwich, right? You have the copper pathways on the outside, but they need to sit on something that doesn't conduct electricity. Guess what? The green board itself. And for a lot of the applications, the board is a composite, and the base layer of that composite, the skeleton, if you will, is this specialized paper. But it's not just sitting there. The specs highlight a property that seems, it seems wrong at first. Guess what it is? Water absorption. Usually, water absorption and electronics in the same sentence, well, sounds like a disaster. Why would you want a circuit board component to be thirsty, you might ask? Well, it's not thirsty for water, it's thirsty for a resin. During manufacturing, the paper acts as a matrix. You dip it into a phenolic or epoxy resin, and if the paper is too dense, the resin just coats the outside. But if it's too porous, well, it just flows right through it. So you need a really specific capillary reaction where the paper soaks the resin right into the fiber structure itself. It's all about impregnation. And once the resin-soaked paper cures, well, it becomes really rock hard. So the paper gives it tensile strength so it doesn't snap, and the resin gives it compressive strength and waterproofing. Think of it like a rebar in concrete. The paper is a rebar. Make sense? But there's another spec that's worth mentioning: cleanliness. Well, we're not talking about coffee stains here. This is more of a microscopic standard, which it is. It's a purity standard. In normal paper making, you might have tiny amounts of metal ions, some grit, things no one would even notice in a notebook. But in a circuit board, a single microscopic conductive particle, bridging two pathways, that's a short circuit. The whole device fails. So you have to refine the pulp to a level of a chemical purity where it's electrically inert and visually spotless. That high whiteness isn't just for looks. It's an indicator that the purity, it shows that you have removed the lignin and other things that could degrade or react with the copper. So if we move down the assembly line here, we're still in the electronics factory, but the Popple's role changes. We go from the material in the board to the material used to make the board, the hot press backing paper. Oh yes. So this is a great example of a process material. The consumer never sees it, but the product itself couldn't exist without it. The manufacturing environment is brutal. We're talking laminating those boards that we just discussed. So high pressure, high speed, it's a hydraulic press. It's also an oven. You're taking layers of copper, that resin-soaked paper, and just smashing them together. Problem is, if you press hard steel directly against delicate copper circuits, you run into trouble. You just basically crushed circuits. So, or you could even get uneven pressure, so which leads to delamination. And also there is a problem with the heat transfer. If the heat hits the board too fast or unevenly, the resin cures wrong. So this backing paper acts as a buffer. It's a thermal and mechanical cushion. It equalizes the pressure across the whole surface and regulates the heat transfer, making sure that the temperature rises smoothly. It needs high temperature and temperature resistance and air permeability. So the temperature part is obvious, but don't burn in the oven. But why does it need to be breathable? Outgassing. When you heat up resins, they release steam, other volatile gases. If your cushion material is airtight, those gases get trapped against the circuit board. They create blisters or voids, so the paper has to be breathable enough to let steam escape, but dense enough to transfer all that pressure. It's a very specific set of contradictions. Tough but breathable, solid but cushiony. And the one stat that really blows people's minds is durability. It can be reused more than 3 times. That is a huge deal. Why? Because when you think of paper in an industrial setting, you think of single use, like a filter you just toss. But this one is designed to go into a hot press, get crushed, and come out ready for the next round. It's a lot about the fiber length and the bonding. If the internal bonds were weak, it would just flake apart after a first cycle. So to survive that kind of thermal shock and compression multiple times, it needs a very high-grade wood pulp. It's built more like a textile than copy paper. And you know, the idea of internal bonding is a perfect bridge to our next section because, well, the hot press paper is designed not to fall apart. There's another product in today's catalog designed to do the exact opposite, but in a very, very controlled way. The layered adhesive tape-based paper. When you think of layered and tape together, your brain might just go, well, that's a double-sided tape, isn't it? But layered here means the paper itself physically separates. And it does. This is a really nice niche, but incredibly complex part of paper mechanics. We're talking about something called Z direction strength. Let me walk you through that. So X and Y are the length and width of the sheet. So the Z is the thickness. Make sense? The Z direction strength is basically how hard you have to pull to separate the top surface of the paper from the bottom surface. In, you know, like 99% of paper applications, you want that to be super high. You don't want your paper splitting. But in this very specific situation and scenario, we're engineering a specific calibrated thickness. You might ask, well, what's the use case for a tape that splits down the middle on purpose? Well, there are a few specialized industrial jobs that take advantage of that. One is in certain splicing and masking operations, for example. Imagine you stick a tape down to protect the surface, you do some process, and then you need to remove the top part of the tape, but leave a very thin layer behind. So instead of the adhesive letting go, the paper itself fails. It fails by design. But fail is the wrong word here because it has to be perfectly clean, consistent split. If it tears in chunks, for example, it's useless. That sounds like a manufacturing nightmare, doesn't it? So it has to be strong enough to get glue applied and wound onto a roll, and so it has to handle X and Y tension well. But the second you pull that Z direction, it has to just give weight cleanly. That's the whole engineering challenge. We do it by manipulating the density and using a multiply process where the bond between the layers is just a little bit weaker than the bond within the layers. The precision has to be incredible. If you're off by just a tiny bit, the tape either fails or falls apart on the roll, or it won't split when you need it to. It's absolutely fascinating to think of weakness as a feature. It's not about making the strongest thing possible. It's about making something with predictable behavior. And predictable behavior is pretty much the definition of quality in engineering. Whether it's soaking up resin, resistant heat, or splitting in half, consistency is a goal here. Now let's pivot away from these industrial uses to something much more visible. This gets into the consumer experience, global regulations, talking about packaging and stuff. The shift away from plastics, you know, the white pollution problem they call. There's a global push to ban single-use plastics, and semi-transparent paper or glass-in is a direct competitor. This is a category where paper is really going head-to-head with polymer films. You know, for years, plastic won because it was clear, oil-proof, and waterproof. Paper was opaque and it got soggy. So how do you make paper act like plastic without coating it in plastic? Well, you deal with the mechanical processing. More specifically, something called supercalendaring. You take like a really high quantity of wood pulp, more specifically 100% bleached sulfate wood pulp, and you run it through a whole series of hard pressure rollers. You're basically like crushing the fiber so flat and dense that the physical pores just close up. So you're not adding like a chemical barrier, you're making the fiber itself the barrier. By densifying like the sheet, you get that semi-transparent look because there's less air scattering the light. But more importantly, you create oil resistance and impermeability. Grease molecules just literally can't find a path through the fiber network. It is categorized as a grade 5 oil-proof for food packaging, and that's huge. Picture, for example, a burger wrapper or something, or the window in a pasta box. And there's also double gloss paper, which gives it like that really smooth surface finish, which is great for printing, and it gives it like a premium, more of a premium feel. There's a specific application that could serve it as an example. It's this intersection of biology and economics. It's called fruit bagging paper. Fruit bagging is a fascinating niche. Most of us assume that those perfect unblemished apples you see in a gift basket are just good luck, but fruit bagging paper is all about bagging the fruit while still on the tree. It's a controlled microclimate. You wrap the young fruit in this special paper. It protects it from pests, wind, and physical damage. But the engineering is really subtle. He has to let in just enough light for sugar production and color, but filter out all the harsh UV that could cause sunburn. And he has to survive rain, obviously. If the bag turns to mush, the whole crop is ruined. But the most critical function is reducing pesticide residue. The bioshield aspect, for example. If the farmer needs to spray the orchard, the paper bag catches the chemical, the fruit inside stays clean. And this leads directly to what's called the passport concept. The packaging is a ticket to the market. Think about it. If you're a grower in Asia and you want to export to Europe or North America, you have to meet incredibly high standards on pesticide residue. If your fruit tests too high, the whole shipment can get rejected. This paper bag also helps ensure that you meet those standards, but it's also about the packaging waste laws like the European Union's directives. Even if your fruit is clean, if it's wrapped in non-recyclable plastic, you could face tariffs or even bans. So far, we've covered a huge range from microscopic precision in a circuit board to the brute force of a hot press to wrapping a pear on a tree, but in every case, the paper is doing active work. That really is a takeaway here. We need to stop thinking of paper as this passive surface you just write on. In these applications, it's an active component. It's insulating, it's conducting heat, it's filtering light, it's mediating stress, and it's doing it all invisibly. You're probably watching me on a laptop right now that has this stuff in it. Or maybe you just ate an apple for lunch that was probably grown in one of these bags. It's just like everywhere. So that's really a good sign of a really good infrastructure, isn't it? It just works so well, you barely even notice it's there. Specialty paper is just tweaking fiber length and density to make our modern lives run smoothly. It makes you think the future of materials isn't just about discovering some brand new element, but rather, getting way better at manipulating the ones we already have. Wood cellulose is one of the most abundant biopolymers on the planet. We're just scratching the surface of what we can do with it when we apply this high-tech processing. So for everyone listening, here's a thought I wanted to walk away with. The next time you peel a sticker or unbox a phone or even just pick up a piece of fruit at the supermarket, just pause for a second, ask yourself, is there a piece of high-tech engineering hiding in plain sight here that made this whole moment possible? And if you look closely enough, you might find wood pulp.